Hi, welcome everyone to the session Mill, a tool built on pure functional programming by Haoyi Lee. We are glad Haoyi can join us today. Without further delay, over to you, Haoyi.
Okay, hello. Hello, everyone. So my name is Haoyi, and this presentation is about Mill. It's a JVM build tool based on pure functional programming. So the agenda for this presentation is three parts. First, we'll talk briefly about what is Mill. Second, we'll discuss why Mill is interesting, both from a kind of user-facing perspective as well as implementation perspective. And lastly, we'll dig into how Mill works. Like, what does Mill do as a build tool that uses pure functional programming, and how does it use it in order to make the build tool experience good for the end users? So first, about myself and about Mill. So about myself, I've been working on open source projects since 2012. I do a lot of projects in the Scala ecosystem. Scala is a popular open source functional programming language. So things like JSON library, file system library, parsing library, and so on for open source. Professionally, I've worked at Dropbox and Databricks working on developer tools. So this is very different from my open source work, things like build systems with Bazel, CI systems, testing systems, multi-cloud infrastructure across Google Cloud, Amazon, and Azure. So I'm also the author of the book Hands-on Scala Programming. If anyone of you want to go and read about Scala, it's a good book to get started. So about Mill. Mill is an open source build tool. It's primarily targeted at the JVM. It supports Scala, Java, and Kotlin. And it also has experimental support for other languages, things like building Python projects, TypeScript projects, Android, and so on. Mostly does the same things as other build tools, but aims to be easier to use, easier to extend, and much faster. So the top line number is Mill is about 2 to 4x faster than Gradle and about 4 to 10x faster than Maven. These are kind of traditional JVM build tools for equivalent local builds. Mill can also serve as an easier alternative to Bazel for large monorepos. So Bazel is very powerful, but also very complex and difficult to set up. So if you have a large project, let's say 1,000 submodules within it, in a big monorepo, multiple languages, some JVM, some Python, some front-end JavaScript, Mill can handle that, similar to how Bazel does. There's documentation at millbuild.org if you want to take a look. But to move on, first, let's look at a small demo. So over here, I have kind of a minimal Mill build. This is a Java project. So over here, we see I have a small like foo.java file. It parses arguments using argparse4j. It renders some HTML using the Thymeleaf templating engine, and then just prints it out. It's like a very simple, just like hello world Java project. There also is a small test suite that does some simple asserts to make sure the HTML is well formatted in the naive case, as well as handling escaping correctly. So the project's not that interesting, and the build file is therefore also not so interesting. So here's a Mill build file. Mill, the build tool, is configured using the build.mill file at the root of a repository. There's a package declaration, some imports. Here we can see that I have a object foo, which is a Java module, and I have a test object within it, which is Java test supporting JUnit 4. Foo also has some third-party dependencies. You can see dependency on argparse4j, which we saw earlier, dependency on Thymeleaf, as well as some dependency on the logging libraries that Thymeleaf and argparse4j use. From here, I can do mill foo.compile at the terminal. I can mill foo.run. You can see it's asking me to pass in the -- text, so let me do that. Hello world. It prints out the hello world HTML. I can do foo.test. You can see it runs a test that we saw earlier in the IDE, and I can do foo.assembly or show foo.assembly, which gives me a executable assembly jar in the JVM, which allows me to run it outside of the build tool. For example, if I want to deploy something, I have this out.jar file I can pass arguments to and have it run kind of outside of your IDE, outside of your build tool. So far, nothing here is that special. All build tools do things like this. Other JVM build tools like Maven or Gradle, other language build tools like Webpack for the front-end world or Poetry for the Python world, all do a similar compile, run, test, assembly. Even interpreted languages now have to be compiled, like Python has type checking, or JavaScript script has type checking. So they all end up being very similar. So that's what Mill is. And the question that everyone will ask then is, if it's so similar to other build tools, why would you want to use Mill? Like, what's interesting about it? And let's discuss that now. There are three main points that you may find Mill interesting from a user perspective. One is that its performance is very good. Two is that its understandability and how we can understand what your build is doing in the IDE is very good. And lastly, the extensibility is much easier to extend than many other build tools. We'll talk about each of these in turn. First, performance. So in order to make a judgment on how performant a build tool is, you need to have a same project built using multiple build tools, and then you can compare them, right? So that's what we did using Mill. For example, to compare Mill with Gradle, we took the open source Mockito code base. Mockito is a popular Java mocking unit testing library. Mockito as a project is about 100,000 lines of code, 22 sub-modules or sub-projects, and it's not huge, but it's also not small. It's quite a substantial project with lots of complexity in it. We ran a bunch of benchmarks against both Gradle and Mill, compiling the same lines of code in the same source files, in the same module structure, in fact, using the same Java compiler. And we find that compared to Gradle, which is the prior build tool, Mill can compile the same code using the same compiler anywhere from 2 to 4x faster than Gradle can. So that's interesting, right? Let's look at another case. We did a comparison of Mill against Maven, which is another popular JVM build tool. For this, we use a Netty code base, which has an existing Maven build. And like Mockito, we translated the Maven build to Mill, took a few hours in an afternoon. Netty is bigger than Mockito, about 500,000 lines of code, almost 50 submodules. And compared to Maven, running the same workflows in Mill versus Maven, you see anywhere from 4 to 10x speed up using Mill. And again, this is same code, same modules, same files. We didn't touch the project at all. We only ported the build file and compiled the same code to using the same compiler, same Java compiler. So how do we do this, right? Well, for example, for the parallel clean compile all benchmark we see here, this is a benchmark command we use for Maven and Mill. So we ran clean, then we ran Maven with 10x parallelism. That's how many cores I have on my laptop. With a bunch of flags to skip tests, skip the various checks to only focus on compilation. And we use install rather than compile because due to some Maven intricacies, compile all doesn't work so easily. And for Mill, we have a similar thing, except for Mill, parallelism is by default, so you don't need to pass in that. And for Mill, tests and linters and such are opt-in, so you don't need to pass, and you don't need to explicitly disable them when you run compile. So we can see what this looks like in practice, right? So over here, if I go to my Netty project here, let me make this a bit bigger. I can run Maven clean compile, and okay, this is a clean that just completed, and now it's running compile all. One thing that people don't realize about Java is that actually the compiler does work very quickly. So typical Java projects should compile around 20 to 50,000 lines of code per second. So a large, let's say 500,000 line project like Netty should compile in about 10 to 20 seconds on a single core. So obviously this is taking out more than 10 to 20 seconds. And a lot of that comes from the build tool overhead, where your build tool, despite being parallel over multiple cores, you can see it using up all my cores here in the top right, adds a lot of overhead, packaging and packaging things, moving things around, and generally slows things down a lot compared to how fast a JVM build tool should be able to compile a JVM project. Now, the JVM is a very performant runtime. Java compiler is a very performant compiler. And yet it takes quite a while to compile a big project like Netty. And it really shouldn't. So you can see I just finished talking. It's about 58.9 seconds, just about 60 seconds, slightly more than the numbers we saw on the slides, but within the same order of magnitude, about 50, 60 seconds to compile everything using Maven. If you do the same thing using Mill, we can see it's much faster. So there's a clean, there's a compile. You can see it's churning away, running. You can see all the things it's compiling in parallel in the bottom. And you're done. It took, in this case, 13 seconds. If you run it again, it'll be faster. Like many JVM projects, Mill is a Java application, it takes time to warm up. So I ran it a second time. Again, I cleaned everything. So I deleted all the compile output and recompiled it. Now it only took 8-point-something seconds. So within the same range that we saw on the slide. So this is interesting, right? Like Mill can compile the same project, same code, same compiler, same language, much faster than existing build tools, simply by removing a lot of the build tool overhead. And this lets us really approach how fast the JVM project should be compiled. Like Java does compile at 20 to 50K lines per second. Big projects like Netty, 500,000 lines, should compile in 10 to 20 seconds. And with Mill, it does compile like that fast, even faster with parallelism, that like we have 10 cores on my laptop. Next thing is interesting to look at about Mill is understandability. And to do this, the most interesting thing is how the IDE support differs between pure functional kind of focused build tool like Mill and kind of more traditional build tools like Gradle or Maven, which aren't built around the functional paradigm. And to explore this, let me pull up my the other project we discussed, which is Mockito. So for Mockito, and so like I mentioned earlier, we have Mockito started using Gradle, and for demonstration purposes, we manually ported this Mockito project to Mill. If you look at the actual configuration, you'll see that the Mockito Gradle build and the Mockito Mill build look very similar. And this is expected because Mill doesn't do magic. The Mockito build is complex. It does have a lot of dependencies. These must be specified somewhere. And so Mill has to kind of follow a lot of the things that the existing Mockito Gradle build is doing. You see this dependency list on the left on Gradle, dependency list on the right in Mill, looks almost exactly the same. And even things like custom tasks. So if I look at this custom like task that takes mock method dispatcher.class and renames it to .raw. If you look at it in Mill, we'll also see a custom task that does almost the same thing. And like Mill, like Gradle has IDE support, so you can like jump to definition. You can ask for the documentation. You can do that in Mill as well. You can see documentation here. So Mill and Gradle, from IDE perspective, both have IDE support in IDEs, in this case IntelliJ. Both represent a lot of the same concepts in your build. So what's the difference here? So what's the difference is when you start jumping around, you'll find that with Gradle, you'll quickly hit a wall where you can't figure out what's going on. For example, let's say I don't know what source_sets.main.java.class directory is. If you've used Gradle for years or decades, you probably will know. If you look at documentation carefully, you'll find out. But let's say I don't want to find out, right? I can ask for documentation here. It doesn't give me anything. I can jump to definition. It gives me some decompiled code. And that's not the worst thing. The worst thing is when I look at what this source directory set thing here is, you'll see that this source directory set is a mutable, global mutable variable. Like I can set it using source dir and source dirs. I can get it. I can override it. And all this documentation is conceptually great. It tells me what source directory set is. But my question wasn't what source directory set is. My question is, what is source sets.main.java? Like, what was it set to? And what am I getting when I call class directories or get on it? So that's something that's very common when working with more imperative code, right? Like you'll go to some variable and the variable will tell you something that's not very helpful and doesn't, and what you want to know is how did the value get into that variable? But the variable will just tell me, hey, I have these fields, or I have this type, but what value do I have? Who knows? So with Mill, looking at the similar code, the experience is different. So let's say the equivalent of the Java here is called compile here. But if I jump to compile, you'll see that not only do I get documentation for what compile is, I get the implementation. And this is interesting, right? Because in pure functional code, if the definition of something tells you all you need to know about it, I don't need to find who's calling the setter somewhere far away. I don't need to like trace through the whole program to figure out who's getting and setting it to find out what it ends up being. It is an immutable value. And so when I jump to definition, that is all I need to know. In this case, compile is called using this zinc worker thing, .worker, called compile Java, with these other values like upstream compile output, all source files, compile class path, and so on. And you can keep doing this recursively, right? Like, let's say I don't know what all source files is. Jump. I have all individual source files fed into Java compiler. I call find source files on all sources. What's all sources? Jump. Here, jump. And you see all sources is sources plus the generated sources concatenated together. What's sources? Well, sources is a source path of this module, which is like the root module. So foo would be in the foo folder in the src subfolder. So compare this to the experience jumping around Gradle builds, where although Gradle also has ID support, because Gradle doesn't have this functional paradigm where where the definitions of things are immutable and tell you what they do, jumping to definitions of things in Gradle is just much less useful than jumping to a definition of things in your build in Mill. And this applies to many other build tools, right? Like in Maven, you can nominally jump around the XML, but XML doesn't tell you what the plugin actually does. In other build tools, you can jump around the YAML or TOML files sometimes, but again, it doesn't tell you what it actually does. Whereas in Mill, anyone who's curious about any part of your build file, like let's say we don't know what super.resources is here, can jump to it and see super.resources has this actual implementation, and this is implementation that you care about. So that's the ID support demo, and why Mill I think is more understandable than other tools. It's not just the fact there's ID support or the fact that it has a statically typed language or a normal programming language. It's by the fact that because the paradigm is functional, makes things like jump to definition and find usages much more powerful than in a build tool that doesn't have a functional paradigm. Lastly, we look at extensibility here. So Mill is interesting because almost all build tools require extensions to plugins as plugins. So you want to do foo, you need a foo plugin. You want to render HTML, I need a HTML plugin. You want to count the lines of code in your module, you need a line count plugin, some such thing like that. In Mill, although plugins exist for more esoteric use cases, often you can just write the code or import the library you need to do the thing in your build. And as long as your task or the logic you're writing is reasonably well behaved, like it's pure, it's functional, it's reproducible, that's all you need to do. So as a demo for this, we look at a kind of contrived use case. Let's say I have this Java module and I want to have the line count of the module sources, and I want to include it as like a text file that the module can read at runtime. So this is a kind of a contrived example. No one in reality is actually going to deploy line count.txt files as part of their production system. But it's kind of representative of all the weird things that you need to do in your production system, right? Like maybe you need to deploy a bill of materials for auditing purposes. Maybe you need to do some special security scanning. Maybe you need to have a custom lint rule that someone's using, or you need to have some kind of custom code generation. There's always all sorts of customization that people need to do in real world build systems. And this kind of line count is just a symbolic representation of something that you may need to do. So let's look at how this can be done in Mill. Over here, let me pull it up. So over here, I have this stub build file on the right. I can do Mill foo.compile because we have the foo Java module here. So you need to compile the build file first and compiles it, and it's fast. So let's say you want to add like a line count task in Mill. In Mill, a line count task is just a method. Any task is just a method, in fact. So I can just say def line count equals task, and I can start referencing other tasks, which are also just methods. So I can say I want foo. I get ID support, which is kind of nice. I can look at the documentation for each of these things. So sources tells me the folders. All sources tells me all the source files fed into the compiler. So maybe I want all source files, which is all the individual source files fed into a Java compiler. So I call the method to get its value. The Mill build file is written in Scala, so you can use all your nice pure functional like map, filter, reduce, and so on. So here I can say f with the file goes to, I want to read the lines of that file path. I want to get the size of the lines, and I want to sum them up. So if you're used to collection libraries in functional languages, you have map, you have sum, you have this kind of operator. This is what we are doing here. And maybe I want to add a bit of documentation, right? Like line count of all the files in this module. So I just defined this task as a method, and I can immediately go and say mill foo.line count. Let's just show the value. Value is 17. That is the number of lines in this example project file. I can do mill inspect foo.line count. You can see all the metadata is nicely shown at command line. The documentation comment is here, the line number and file name is correct. The inputs for the all source files are lifted out and shown so you can inspect them. And now I have a line count task just by writing a simple method with like 4 lines of code. Now, if I want to wire up this line count task into the existing resources of this module, I just need to override the resources task. I can say override def resources. Again, you can use your IDE to look at what things you can override and figure out, hey, okay, I want to override this resources task. It says the folders where the resource files for this module live. Yeah, and I don't need the resources to be seen by the compiler. So this is the one. And I can say this is, again, just a task to put out resources, except I want to write to the destination folder of this task, line count dot toString. And I want to say append to the resources a reference to my current destination folder. I think I need to say, give it a file name like line count.txt. So now if I can say mil foo show foo.resources. You can see that there's 2 files now. There's 2 folders now. There's a traditional like foo/resource folder that most Java projects have. But because I appended this generated code folder, we also have out/foo/resources.destination. I can look what's in that folder. There's line count.txt. I can look at what's line count.txt. It's 17. And now if I do mil foo.run, sorry, run, not rah, you can see that the example code, which we kind of glanced at earlier, is able to access and print out the line count at runtime. So this is interesting, right? Like everyone already knows how to define methods that call other methods. And that's what we're doing here. Everyone already knows how override works from Java 101 or Python 101. Everyone knows how super works. Like you learn super in high school or in college when you learn programming. And all you need to do is just write some normal code in a functional style, like returning the sum here, returning the resources with the new resource path appended. And that's all you need to do to define, customize your mil build with custom tasks, override tasks, and so on. Let's go one step further. Let's say instead of line count.txt, I want line count as a HTML file. So mil doesn't come bundled with like any HTML templating libraries. You can say import org.timeleaf. But if you try and build this, you'll get the error. It says timeleaf is not a member of package org. But mil allows you to easily import anything from any third-party JVM libraries using this import $ID syntax. So you can say I want import org.timeleaf timeleaf 3.1.1.release. And now if I run the project, you can see that this compiles successfully. And I can say I want to import the template engine, import the context, and instead of just the line count as a task returning number, I want line count HTML as a task returning HTML file. So I can use it, let's say, new template engine dot process, and the template string, there's this timeleaf syntax that the library has documented online. I'm just going to reproduce it here. And just going to say $text. And I need to pass in a context. So I need to say context equals new context. Context.set variable. Text is line count dot toString. And I can say, instead of depending on line count dot toString here, I'm going to depend on line count HTML in my resources override. And now when I do foo.run, you can see that I am able to render HTML using this off-the-shelf third-party library as part of my build at build time. So if I inspect this file, I can do mil show foo.line_count HTML. We can see this is the HTML that got rendered at build time. And all of this without any plugins. So not all of you are JVM or Java developers, but for any Java developer who already has used Timeleaf, for example, as part of their day-to-day job, who already knows how to operate all these open source libraries, mil allows you to just directly use those open source libraries and use your knowledge of how to use these open source libraries as part of your build. So there's no mill time leaf plugin, there's no mill line count plugin, there's no mill append file to resource plugin. You can just write the code to do it yourself in a very concise, pure functional style, and it just works. So that's the extensibility angle of mill, where rather than having plugins, you have to deal with the plugin interface and plugin ecosystem. You just write this pure functional code and use any library you want, and it will just work as part of your build. So that's why mill might be interesting to people. For those of you who are using Java, maybe you're more familiar with this. For those of you who are not using Java, the same problems apply to many other language build tools, whether using Webpack, whether using NPM, whether using Bazel. All of these have the same problems around performance, the same problems around understandability and discovery, the same problems around extensibility. And mill tries to solve some of these problems in a kind of nice way using the ideas behind pure functional programming. So next, we look at how does mill work? Like how does mill achieve this good performance, good understandability, good extensibility, and so on? So there are a few ideas, core ideas behind mill. One is that modules are objects and tasks are methods. So many build tools have this separate idea of, you have your programming language, whether it's pseudo Python like in Bazel, or whether it's XML like in YAML, or like in XML like in Maven, or whether it's Groovy like in Gradle or Kotlin. Many of these build tools have this idea that modules and tasks are something separate, right? Like you have to register modules, if you register tasks, they're hooks. You can define methods and objects, but in the end of the day, you need to do this task and module stuff. Mill is different, where modules are just normal objects in your build program. Tasks are just normal methods in your build program. So for example, when I say object foo extends Java module is a class or a trait in Scala, but it's basically a class. And a class has methods we inherit, and these methods call each other, like in a simplified version like this. Like maybe the assembly method calls class path and resources, class path calls compile depends on sources, and uses the sources as part of its implementation. So in mill, the method call graph is the task graph. So this is how the methods depend on each other. This is also how the build graph looks like. And when I add methods to this Java module, like any class in any programming language, you can add methods to the class when you subclass it or extend it. You can override methods. So when I add new methods like line count, which calls all source files, or when I override existing methods like override resources, which calls line count and super resources, this changes a call graph as you would expect in the top right. It kind of splices these two methods in, and it changes the task graph in exactly the same way. So once we have this task graph, mill is able to do intelligent things. For example, mill can see that foo.compile and class path are separate from foo.line_count and foo.resources. And thus, the blue tasks up here can run in parallel with the red tasks down here. In contrast, foo.assembly depends on all of them, and therefore foo.assembly has to wait until all of these finish before foo.assembly can start. Mill can assign the different tasks places on disk to store its cache metadata or file output. So like, for example, line count, in order to cache output so we can avoid recomputing it, we give the foo.line_count task out/foo line_count.json file that it automatically writes its output to. Same for compile and assembly, have these JSON files containing their metadata, as well as this destination folder that contains the file output. Because as you know, most build tools, they work with files on disk. So although files are technically I/O and not quite pure functional, we need to manage them. And so we give you a nice folder for you to manage them and put them in. And because the tasks are pure functional, mill can intelligently do incremental rebuilds. For example, if you touch the resource folder, which we've overridden, so it's now called super.resources, mill can see that, well, we do a breadth-first search downstream in the task graph. Foo.resources is downstream, that needs to be recomputed. Foo.assembly is downstream, that needs to be recomputed as well. But foo.line_count, foo.compile, foo.classPath, all those we do not need to recompute. And because the tasks are pure functions of their input, we can safely reuse the output without worrying about reliance on some side effect that the task may be doing. That's common in many other build tools or things like shell scripts. So what's interesting about this mill build config here is that you see we define some custom tasks like line count and override. We get nice things like parallelism, caching, incremental recomputation. But you look at the task definitions here, there's nothing to do with parallelism or caching or incremental recomputation at all. All you have is some pure functional code that says a line count is all source files mapped to the lines size.sum. Resources, I create a new file and return it as part of my resources path. You don't see threads, you don't see semaphores or locks, you don't see futures or executors, thread pools. From the caching side, you don't see computation of cache keys, you don't see cache reads and cache writes, you don't see writing to cache files and all that. All of that is managed for you by the mill framework. And so you can just write your kind of naive, pure functional code in mill, methods calling other methods. And as long as your tasks are pure, which is usually the case with to a great degree, you can just rely on mill to do all the other fancy stuff for you. Your parallelism, your caching, incremental recomputation, cache invalidation, and you don't need to worry about any of that. The mill runtime will take care of it. So that's the idea of how modules are objects and tasks are methods. Next is the reliance on the pure functional nature of your build graph. So most build tasks are in fact pure functions. So what does a build tool do? Well, on the JVM, you resolve dependencies to make dependency jars. You run code gen on IDL files to get generated sources. You compile sources and dependencies to make class files. You test the class files and dependencies to make test results, and the list goes on. So if you actually look at this in all of these steps are basically pure functions. Now there's a bit of an asterisk here, like you are reading and writing to files. You are like, you may be calling sub-processes and stuff, but logically, semantically, you can see that all of these follow the pattern of do something to inputs to generate output, do something to inputs to generate output, do something to inputs to generate outputs. And this is a slide that's kind of talks about the JVM names of things, that we call them jars or IDL files or executable assemblies. But the same applies to any other programming language too, right? Like in Python, your jars are called wheels. Your executable assemblies are called PEX files. Your class files may be called PYC files. But otherwise, they are very similar. And this kind of pattern of the fact that almost every build task is a pure function applies to almost every programming language and ecosystem. And mill takes advantage of that. This do thing to something to make inputs to make output. In Pythonic pseudocode, it looks like this. Mill, the syntax is slightly different. We need to wrap in this task wrapper in order to do what we want. But logically, we are saying that the output is a pure function of its inputs. And once we accept, or once we can assume that the outputs are pure function of inputs, that is when we can do interesting things. So like we know that there's no side effects, no mutation of global state. And so we can take this graph and do the incremental computation because we know that it's not going to rely on something that always needs to run. We can take this graph and do the parallelism because we know that they won't stomp over each other. The different tasks won't stomp over each other, kind of fighting over the file system in parallel. We know we can safely save the result of a task to a JSON file on disk and load the result later and reuse it because the task is pure and everything that the task does is encapsulated in that JSON file that is a serialized return value of that task. And lastly, jump to definition therefore tells you everything you need to know about the task because there's no mutation where someone's going to set it here and you're going to read it later. When you jump to a definition, that is what the task does, and that's all you need to know. And if you want to recursively jump upstream, you can do so as well. So like this is just another kind of more elaborate example of what we saw earlier. Like Gradle, you have source sets on main to all sources. Main it's called foo to all source files, but it's basically the same thing. In Gradle, you jump and you hit a wall where you just get this mutable variable that just says you can set it, you can get it, but you don't know who's setting it or who's getting it. Mill, on the other hand, when you jump to it, you keep getting useful information because all of these mill tasks are pure functions of their implementation and inputs. And so when you jump to them, you see the implementation, you can see the inputs, and you can keep jumping and exploring what these tasks do rather than hitting a wall like is the case in Gradle and many other build tools that are not based around the pure functional paradigm. The last interesting thing to discuss here is bridging pure functional programming with build tooling. So, if build tools are so similar to pure functional programming and like we benefit so much from pure FP, why aren't they all written in Haskell? Like the answer is that build tools have many non-pure FP concerns that they have to deal with, that your naive pure functional programs don't deal with. And build tools do need to deal with them because that's what people actually need to do in their real world builds. Right? There is some real complexity here that your build needs to manage. And a lot of it doesn't quite fit so nicely into a pure functional paradigm. For example, we mentioned files and disk I/O a number of times. The problem here is that build tasks need to read and write files to disk, right? So you have compilers, bundlers, packagers, all of them read and write files to disk. No one's going to run GCC in memory on all your source files in memory and generate a whole bunch of binaries in memory that you run your linker on in memory and execute your output binary in memory. All of these tools and build systems work on disk for good reason, right? You can't fit all that stuff in memory. Memory is not cheap compared to disk. And then many of these build artifacts are quite large. So we already kind of touched on this, but what Mill does here is that Mill says, okay, we can't stop you from reading and writing to disk. But what we can stop you from doing is this shared mutable state problem with the disk, right? Like, what's the problem with reading and writing to disk? That in parallel, if you're in parallel, you may stomp over someone, that you may have some unexpected dependencies, you may have race conditions on disk. Mill says that I will give every task a dedicated folder they can write to. So line count has a line count.desc file folder, resources, the resources.desc folder, and so on. Only one task may write to each desk folder, and only downstream tasks may read from it. So with these two invariants, we basically turned the file system from a shared mutable state problem into a not shared, not mutable state problem. It just becomes kind of immutable state that part of the return value of each task. So although we still need to read and write the files, like over here, we're reading the lines from the all source files. Over here, we're writing to the task destination folder. We can be confident that when we read these lines, no one else is touching those files and mutating them. We can be confident that when you're writing line count.txt here, no one else is going to race with us and overwrite our value accidentally. These files just become normal immutable values that they're not really in memory like your normal immutable values are, but you can treat them as if they are in-memory immutable values, and you get all the benefits of pure functional programming despite having a bunch of files being read and written to disk. Problem two, right? Like build outputs need to be cached for performance. So you don't have to recompile the whole world every time you add a print line. But pure functions, what can you do with a pure function? The only thing you can do with a pure function is run it. You can't cache parts of it automatically. You can't inspect it. And Mill says that we'll let you write your pure functions, and Mill will handle the caching. Mill will handle the saving of the pure functions to disk in JSON files for you. So if we let the user start writing things to disk, they have a chance of screwing up. They have a chance of having race conditions, all the other caching problems. Reading and writing a cache is naturally a mutable operation, right? Like you can't screw it up and then you get confusing results. Mill says that Mill will handle it. So the user just treats these tasks as pure functions. You return a value, and Mill will make sure that the caches and invalidation all gets done right on the back end. So although the implementation of the Mill runtime has all this mutation and I/O inside, from a user perspective, you don't see it. You just return pure functions and write pure functions and return values. This is not dissimilar to how languages like Haskell work, where your Haskell code is pure, but the Haskell runtime has all the mutation and side effects going on within it. The last thing to look at is reconfiguration. So build pipelines are often reconfigured in ad hoc ways, like over this module has custom compile option. That module has some custom code generation going on. This module, there's a linter that team is experimenting with, but we haven't gotten confident to roll it out across the organization. That module needs to have a custom deployment artifact because we're trying to integrate with some new vendor, and the vendor has some weird Docker format that isn't used across the rest of the ecosystem. So while this may seem ugly, and it is ugly, this is the reality of many build systems, because you need to manage this complexity that is part of your real project complexity. And what Mill says is that in order to make this stuff reconfigurable, rather than using opaque functions to define your build pipelines, we use classes, for example, Java module. And anyone who learned Java 101 or Programming 101 knows classes have override and super. And this lets us very easily and in a very convenient and familiar way override and customize parts of our build pipeline. For example, splicing in this food.line counts, food.resources, while still being part of the larger build pipeline that we want to reuse. So this is not something you want to do kind of ad hoc in a lot of your production code, but in build code where the exceptions are often more common than the norm. This is a very handy way that Mill can allow that while still being very familiar and easy to understand for users. So that's bridging how Mill bridges pure FP with build tooling. So to wrap up, like the core ideas behind Mill is that modules are objects, tasks are methods. A build graph is a pure functional program. And we need to, despite being pure functional, we need to bridge this pure FP with the messy realities of build tooling around files, around caching, around overrides and reconfiguration. And Mill does this, and that's why Mill can be a useful build tool despite leaning heavily on pure functional programming. So I think we're done with the talk. I hope we found this interesting. This is kind of a summary slide with everything we discussed earlier. And the documentation is in the bottom left if anyone wants to check it out. And I guess we have 5 minutes. You can take questions if there are any.
Hey, thanks, Haoyi, for sharing your experience with us today. So anybody from the attendees, if you have any questions, you can put your questions in the Q&A section and Haoyi can try to answer them.
I see someone says, would you recommend it to a curious .NET dev? Right now, Mill doesn't have .NET integration. The languages it supports are kind of shown here. You could experiment with it, but it definitely is not kind of production ready for you to use with .NET code bases. That's something that will need some kind of R&D and things to experiment with before we can figure out whether it'll work or not. Sean Corfield says that in Clojure, you have similar things. Yeah, I think it's the concepts behind pure functional programming are very relevant here. But I think a lot of the difficulties in the details of how you actually execute. Writing pure functions is great, but how do you do things like incremental recomputation when input file changes? How do you do things like someone edited the body of a task method and decide what tasks need to recompute? Or someone edited some helper method and decide what tasks need to recompute. So that's, I think, the real challenge here. And if you try and do naive pure functional programs, you always will hit these problems. Like you'll say, hey, why is my whole build recomputing every time? It's getting slow. And then you start needing to look into caching, incremental computation, parallelism, introspection, all those things. Yeah. And yeah, Ned Wu says great sharing. Yeah, thank you. Yeah, I hope you find these techniques interesting. Cool. I guess we are done.
Yeah, I guess
1 minute early.
Thank you, Haoyi.
Right, thank you.